In our previous video, I talked about the concept of pixels and the concept of colors within a pixel. So X and Y represents the value of a pixel, and an image has a width and a height. And then we talked about colors. So essentially every pixel is represented by 4 different channels: red, green, blue, and alpha, each ranging from 0 to 255. Now what we can do is use those channels and use that data to hide messages. And that's the concept of steganalysis. So let's look at the letter A. So the letter A can be represented in ASCII by the value 65. This is capital A. And then in binary, this is going to be 1 0 0 0 0 0 1 0. So this is, remember, your base 2, 2 to the 0th, 1st, 2nd, 3rd, 4th, 5th, 6th, and 7th power. And this will correspond to a 1. This will correspond to a 64, equals 65, check, we're good. So these correspond with each other. All right, so we have A equal to 65, which equals this, these bits. Now, we also have an image. And let's say that this image is going to be it's going to be 4 pixels in width and 3 pixels in height. So this is your X going to the right, and your Y going down to the bottom. So this first pixel is 0 0 1 0 2 0 3 0, and then Y 1 0 1. Sorry, my apologies. 0 1 1 1 2 1 3 1, and then 0 2 1 2 2 2, and 3 2. So these are each of the pixels in an image. Now let's say every pixel in this image is white, and that represents a RGBA value of 255, 255, so that's your red, your green, 255, blue, and alpha, 255. So that is the color white. Now what we can do if we want to embed a number like, or a binary number like A with a representation of 0, 1, 0, 0, 0, 0, 0, 1, we can do 3 things. We can choose a channel, and we can say we're going to embed this message in the red channel. So here, red of 255, we're going to say that value varies based on the value of where we're at within this bit string A. Now, what we can do, open up a new slide, is say, so we have a binary value of 0, 1, 0, 0, 0, 0, 0, 1. We can break this up and say that value 0, and this isn't an image, this is just a table, we're going to put each of these bits, this is going to go in 0, 0. So pixel 0, 0 is going to hold this piece of data. Pixel, my eraser going here. There we go. So x of 0, y of 0 will hold this first bit. X of 1, y of 0 will hold the second bit. 1. One, 2, 3. All right. So this first bit will be stored in pixel 0, 0. The second bit will be stored in pixel 1, 0, third in 2, 0, fourth in 3, 0. And then we go down to the next row. So if you imagine the image, this first set of 4 goes in the first row. So y equals 0, y equals 1. This second set of 4 goes down in the second row of the image where y equals 1. And then what we've done is we've placed this in the image. So now, if we go back to our other image, we know that this first 0, 0 is going to house the number 0. This is going to house 1. This is going to house 0. This is going to house 0. And now jump down to the second row. This is going to house 0, 0, 0, 1. So we need 3 states, all right, in our algorithm to know that whether a slide is showing a 1 or a 0 or no value at all. Because remember, we have 12 pixels in here, but the letter A is represented by 8 binary bits. So we have 4 pixels that really don't do anything, don't mean anything, don't contain any message. So we're going to do a few things. So right here, if the value, so if the bit equals 1, we're going to set red equal to 1. If the bit equals 0, we're going to set red equals 0. And then no bit, red equals 255. So we're going to do 3 things. If there is a binary value, so 0, red is 0. If there's a binary value 1, red is 1. And if there's nothing, if there's more pixels than there are bits we're trying to encode, red will be 255. So what does that mean here? This means right here, red equals 0, red equals 1, red equals 0, 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 red equals 1, red equals 255, because again, these last 4, there's nothing. Red equals 255, red equals 255, red equals 255. All right, so that's how an image would look. Now, what if we were to draw this image? What would it look like? So we know that we're encoding, we have a blank white image, and we're going to encode the capital letter A into it using this algorithm, where if the bit is 0, red equals 0 in the red channel. If the bit is 1, red equals 1. If there's nothing, red is equal to 255. All right, so this one right here, let me get my pen back. We know that this first pixel 0, so this is going to be teal. All right. this second pixel is going to be teal. So the value of teal, it happens to be 0, 255, 255, 255. And this will be teal. And this will be teal. And this will be teal. And I'll draw the values back in a second. I just wanted to get you a bit of an understanding of where we're going. And then more colors. I'm going to embellish this a bit. This is going to be a bit of a lighter teal. And this is going to be a bit of a lighter teal. I feel like Bob Ross right now. And the rest of the image is going to be white. Now why? Because this pixel color is 0, 255, 255, 255. This pixel color is 1, 255, 255, 255. This pixel color is 0, 255, 255, 255. And so on and so forth. This one is 1, 255, 255, 255. And down here, these pixels contain no value for A, or for the bits we're looking at. So this will be 255, 255, 255, 255. And so on and so forth. So what did this correspond to? Well, again, up in the top, we had 0 in 0, 0. In 1, 0, we had a value of 1. In 2, 0, we had a value of 0, 0, 0, 0, 0, 1. No value, no value, no value, no value. So this goes back to the bit value of 0, 1, 0, 0, 0, 0, 0, 1, which corresponds to the value of A. So if you were to see this image where you have our algorithm, and then you had a bunch of teal and a final strip of white at the bottom, this would represent the letter A. Now, I've used two different shades of teal here. You wouldn't normally notice the difference because we're talking one value in red, green, blue, value difference here. So it would be negligible to the human eye. But essentially, that's how it works. Steganalysis can use a bunch of different algorithms. We've chosen an algorithm here where we are taking a single pixel, choosing a channel, and applying bit values to that channel. You can come up with a ton of other algorithms, come up with your own. This, obviously, if you saw this image, you'd catch right away, there's something weird about it. But essentially, that's how steganalysis works. So when we're reading this back, we would say, okay, what's the value of the red channel? If it's 0, then that bit's 0. If it's 1, then that bit's 1. If it's 255, we're done. And then we would convert that bit value back to a number, and then that number to a string. So that's the concept of steganalysis. You can, again, choose whatever algorithm you want, but it's steganalysis using an algorithm where we are setting the bit. We started with the letter A. We broke that down to its constituent ASCII numerical value, which is 65. We broke that down further to its binary value. We applied that binary value to be the value of the red channel within each pixel of an image. If there was no binary value or bit value, we set the red channel value to 255. We walked through essentially what it would look like if you viewed the image. And then we walked through how we converted it back. Again, we take each of the values in the red channel. We put that into a bit value. That bit value goes into the numeric value of 65, which then gets converted to the uppercase letter A. And that's about it. That is an overview of steganalysis and how it works. You'll be able to experience this in your lab this week. But again, it's a very interesting concept. It's a little more sneaky than sending an encrypted piece of text, where you look at the encryption string and you're like, oh, that's probably encrypted text. Someone's trying to send a secret. You could put this on an image and no one would ever know that you're sending a secret message to someone else. But you're using steganalysis to do so, and it's a very interesting way to communicate with other people.